Good morning, everybody, and welcome back to Physics 101. So hopefully everybody can hear me. I'm going to talk a little bit about the test at the beginning, and then if we have time at the end, we might have some time at the end, I can answer some more questions. Someone was asking about the solution in sapling. I believe you should be able to see homework 2 solution, the one for chapter 2. If not, there's a whole separate practice assignment where I just copied it over again, and you can see all the problems and do them all again, and you can give up and see the solutions. And I just did the same thing for the chapter 3 homework. So just go into the second one that's called copy for practice, I think it's called. And you can go in and give up, and you should be able to see all the worked out solutions also for the chapter 3 homework. Yes, this is in sapling. Okay. So also I wanted to point out that Rasul is not with us today. He's not feeling well. So he won't be able to answer your questions in the chat. I will try and check them periodically. I can't answer questions while I'm talking. That's just not possible. But I'll try and stop periodically and look at the chat and try to answer some questions as I go. And if not, I can try and answer all the questions at the end. So no, not all of everything. I mentioned this, the midterm covers more material, okay, than we're being tested on. You're only being tested up through the end of our chapter 3. That midterm, as you can see, also includes forces and other topics that we have not covered. Okay, I don't have a test that matches what you guys will be doing. Okay, so, and I would say that some of the sapling is more difficult than the test, and some of it isn't, because the difficulty of the sapling varies. All right, so let's save the rest of the test questions until the end. All right, and now we're going to do a little bit of physics and talk some more about Newton's laws and chapter 4 content. So let's find our slides. Oh, actually, before I do that, I just also wanted to point out that there's a whole bunch of logistical information about the test that I posted in Canvas. And it's really important that you go and read all of this and make sure you understand all of it. And if you have any questions about it, if you have a general question, you can put it in Piazza. And if you have a question that's personal to you, you can ask it in the Canvas email. Okay, I think most questions though, you should be able to ask in the Piazza, please. Okay, that way one person can ask it and I can answer for everybody. It's a lot more efficient, and you're likely to get your question answered more quickly that way. Okay, so let's switch over now to, so we're going to stop sharing that. Okay, and now we're going to switch over to our slides here. Okay, so we are doing our second lecture now on chapter 4 on forces. Okay, so we've already done 2 of Newton's laws, and this comic here actually is about Newton's first law, right? An object in motion remains in motion. Okay, so so those guys would not do very well on their Newton's laws test. So so now we're going to do Newton's third law. And Newton's third law says, if an object exerts a force, if object A exerts a force on object B, then object B exerts a force on object A that has exactly the same magnitude, but is in the opposite direction. And sometimes this is referred to as the action-reaction law. For every action, there is an equal and opposite reaction. I don't like that way of talking about it because it doesn't define that an action and a reaction, that they're referring specifically to forces, and they're not talking about what those forces are acting on. And both of those things are really important. This law seems very simple, but it's actually a lot more complicated than it appears. So I thought we would start by looking at some examples here. Okay, so of Newton's third law in action, because we have Newton's third law to thank for helping us get around on a daily basis. For example, if you look at the first example here, we have a person walking, and you can see what sometimes we refer to as the action-reaction pair here. How do you walk or run? How do you move? Well, you need a forwards force. Where does that forwards force come from? Well, it's because you're pushing off the ground. So you exert a force on the ground with your feet, and then the ground pushes back on you. So you push backwards on the ground, and the ground pushes you forwards with an equal and opposite force. So there's one example of Newton's third law. Another example would be a boat that has a motor. Okay, and in this case, the motor causes the propeller to spin. The propeller exerts a force on the water. So there's a force on the water by the propeller, and there's an equal and opposite force on the propeller by the water. And then because the propeller is attached to the motor, which is attached to the boat, that pushes the whole thing forwards. Similar situation with rockets, except it's a little bit different because rockets actually essentially force a bunch of gas to expand very quickly and force it back down outwards out the back. Okay, and so you get a force on those gases by the rocket, and then you get the equal and opposite force on the rocket by the gases. Okay, and then the fourth example we have here is a wing, okay, on say a glider or something that's moving. And in this case, we're looking at the lift going on here, and we've got the force on the wing by the air and the equal and opposite force on the air by the wing. So you can see in all four cases, the things that are really important to remember are that these two forces act on two different objects. Okay, one acts on object A and one acts on object B. So they always act on different objects. Okay, and that the two forces have the same magnitude in all situations. So it doesn't matter which situation, what's going on. Okay, once you've identified the Newton's third law force pair, okay, force A on B, force B on A, those two forces will always be equal and opposite. And this can be really useful for figuring out what's going on in various physical situations. Okay, so I thought we would try a poll question on this one. So why don't you have a look at this while I make up the poll. Okay, so there's our poll. All right, so what's our question? So our question is, so you have a book that's sitting on top of a table. And we know the Earth pulls downwards on the book with a force due to gravity equal to the weight of the book. And the question is, which of the following forces is the equal and opposite force, the reaction force, when you apply Newton's third law? Okay, and we've got four choices: the normal force on the book by the table, the force due to gravity on the Earth by the book, the normal force on the table by the floor, and the normal force on the table by the book. So there's a lot of different forces that you can think about here. And we're trying to figure out, remember, we want the Newton's third law pair force. So the equal and opposite force to the force due to gravity, okay, on the book due to the Earth. All right, I think we're going to do maybe 10 more seconds on this one. So go ahead and guess if you're not sure. All right, so we've got 5, 4, 3, 2, 1. All right, so let's see what everybody thought. All right, so it looks like the majority think it's A. And then we have the next biggest group think it's D. And then the next biggest group after that thinks it's B. Okay, so let's actually have a look at this one and see what the answer is. All right, so here's our scenario. Okay, there's our book on the table. There's the normal force of the table on the book, and then there's the weight vector. So now what are we looking for? We are looking for the reaction force, or the Newton's third law pair force, that goes along with the force on the book due to the earth, because that's what the force of gravity is, right? Earth pulls downwards on the book with a force due to gravity. Okay, so according to Newton's third law, so if this is the force on the book due to the earth, you have to flip the two objects, right? Because remember, Newton's third law said the force of A on B is equal and opposite to the force of B on A. So in this case, the Newton's third law pair, the reaction force, is actually the force on Earth due to the book. Okay? It's not actually the normal force. Okay? So that's one of these cases where this law can be confusing. Okay, so because it's true that the normal force and the force on Earth due to the book are the same size, right? Because the force on Earth due to the book is the same size as the force on the book due to Earth, but in the opposite direction. And the same is true for the normal force when you have a book sitting on a horizontal surface like this, okay? But the normal force is not actually the reaction force here, okay? It's always got to be, if you say, I know what the force of A on B is, then the reaction force is always, what is the force of B on A? You have to flip the order of those two things, okay? So that's really important to remember when you're doing this, okay? So the normal force here, what is that? That's the force of the table on the book, okay? That's not the force on the Earth due to the book. Okay, so now we don't usually think about the force on Earth, right, due to objects, right? Like we're all exerting forces on the Earth right now, and we don't usually think about that because, well, first of all, Earth is a sphere, and all of those forces are pointing in all 3 dimensions and essentially would cancel each other out. Okay, and they're also quite small, so they don't make a big impact on the Earth. So we don't actually usually even consider the force on Earth due to the book, but you could go and analyze, you know, what kind of acceleration the Earth would get from that force, and you would discover it's essentially 0. Okay, so what would be the pair force for the normal force on the, so the normal force there is the force of the table on the book, right? So the opposite, or reaction pair, Newton's third law pair for that one would be the force of the book on the table. So that would be A, the normal, sorry, no, it would be, yeah. Sorry, it would be, not A, it would be D, sorry, D, the normal force on the table by the book. Okay. Yes, a normal force can be a reaction force. It's just not the reaction force to the force due to gravity. Okay, so for example, like I just said here, the action-reaction pair for the normal force, you would have the normal force of the table on the book and the normal force of the book on the table. Okay, so let's do another one just so we can get a little bit better So this one is a bit trickier than the last one, and the last one was already kind of tricky, right? Like I said, we're going to spend some time on this concept so that we really get a good handle on it, because concepts are very important in physics, and we need a good handle on understanding the concepts so that we can figure out how to do problems with the concepts, okay? So essentially, the pair force of normal forces are never weight, okay? Because weight is always due to gravity, and the normal force is always due to a surface. All right, so let's start another poll for this one. We've got our 4 choices again. Okay, so what do we have here? So now we've got 2 blocks side by side. So 2 blocks with one's bigger than the other, with big M greater than little m, are on a frictionless horizontal surface. And the question is, if you apply a horizontal force either toward the right on big M or toward the left on little m, it will cause both blocks to move together with the same magnitude acceleration a. And the question is, now you're trying to figure out what's the magnitude of the contact force that one block exerts on the other. So that's what we're trying to figure out. Okay, and the question is that contact force, is the force of big M on little m, and likewise little m on big M, which would be equal and opposite, okay, is the size of that, okay, is it larger if the force F is applied toward the right on big M, or is it larger if the force is applied to the left on little m? Is it 0 in either case, or is it the same in either case? Okay, so remember, we're comparing, all right, if we apply the force towards the right or towards the left, okay? Right, if you apply the same force, okay, either way, okay? So you're essentially applying it to the system here, right? Okay, how does that impact the contact force? Does it make a difference? All right, I think we'll try 10 more seconds on this one. So if you're not sure, go ahead and guess. All right, we'll do 5, 4, 3, 2, 1. All right, let's have a look at the answers. So what do we got? It looks like the largest group thinks that the answer is D, that contact force would be the same in either case. Okay, and then the next largest group is voting for B. It's larger if the force is applied towards the left on little m. And then there's a small group that's going for A, and three people going for C. All right, so I'm going to tell you that the answer is not D. Okay, this is another confusing one. All right, so I'm gonna give you a bit more information, and then we'll give it another try. All right. So here is a force pushing on big M. Okay, and if a force is pushing on big M like that, then you'll get an acceleration to the right. Correct? All right. And so that means that there's a contact force between the two blocks, which I labeled as the force of big M on little m, okay? And that force, okay, would be equal to m times A, right? Okay, because that contact force, that force of big M on little m, is the force that's causing little m's acceleration. It's the only horizontal force, if there's no friction, acting on little m, okay? And that's causing little m's acceleration to the right with an acceleration equal to A, okay? So maybe we'll just do this, I think we'll just try and do this in the chat. So if I tell you the answer is not D, okay, which one do you think it is then? So why don't you go ahead and vote in the chat. Okay, so we've got lots and lots of B's now that I told you that the answer wasn't D. Okay. Wen Long, you had a question? Do you want to type it in the chat, or did you not have a question? All right, well, let's try and explain this one while you type your question. All right, so now if we look at the opposite situation, now if we flip it, okay, and we say, what if we applied F towards the left on little m, then we get an acceleration, same size acceleration as before, because it's the same force and it's the same two masses, but in the opposite direction, okay? And now we have the F, the force of little m on big M, that contact force, and that's the force that's going to cause the acceleration of the big mass, okay? It's going to cause big M to accelerate to the left now with an acceleration equal to A, okay? And so that means that in this case, the contact force is big M times A, okay? And we know that big M times A is greater than little m times A, because A is the same in each case. And so that tells us that yes, the answer is B, okay? That this contact force will be larger if the force is applied towards the left on little m. Okay, other questions on that one? So this is a matter of looking at the object. In this case, we're looking at the second mass, not the one that the force F is acting on, but the other one, and saying, what do I know about that object and what has to be true for it to have that acceleration A? Okay, so we're going to move on now. Why is it big MA? That's because big mass M is accelerating to the left with acceleration A, and the only horizontal force that could cause that acceleration is the force of little m on big M. Okay, well, you wouldn't say the net contact force is zero because one contact force is acting on the big mass and one is acting on the little mass. Okay, so I would not say that. I would say that the contact force right here, in this case that we're looking at right now, the contact force is what causes big M to accelerate to the left, because that's the only force acting on big M. F is not acting on big M. F is acting on little m, okay? In fact, what's acting on little m is F acting to the left and a contact force from big M on little m acting to the right, and that net force would then cause the acceleration of little m. All right, it helps, like in this case with two objects, you would want to draw two separate free body diagrams, one for each of them. And in that case, big M would only have one force on it, but little m would have two forces on it. Okay, we'll do some more examples hopefully, and you'll see some there were some in the pre-lecture, and you'll see some in the homework to play around with. All right, tension. So tension is an interesting force, and we're essentially only going to be dealing with tension in light strings. Okay, so tension forces, basically, if you're only dealing with a light rope, a light string, are always going to be equal and opposite at either end. So as you can see with these two people playing tug of war, okay, that the tension force in the rope, okay, on the left side is pointing in the positive direction and it has a magnitude T, and the tension force acting on the other person, person B, is pointing in the left direction, so opposite direction, right, but has the same magnitude. And so a vector that points in the opposite direction but the same magnitude would be minus T. Okay, so these two tensions are the same size but in opposite directions. Okay, and that's the main thing to keep in mind when you're dealing with tension in problems. Okay, and this is true whether the rope is at rest or whether it's moving. So even if our two guys are moving like this, there they go, that still, the two tensions will still be equal and opposite at either end of the rope, like that. So I thought we would do a tension pole question to practice this. So let's see. We've got 4 choices again. Okay, so we'll start this one going. All right, so now we have 3 blocks connected by light ropes, 3 blocks of mass 3m, 2m, and m. And this is the picture I showed you on Monday that I told you would come back again. And they're pulled such that they have a constant positive acceleration a. So they have an acceleration in the positive direction, as drawn, towards the right. And the question is, what is the relationship between the magnitudes of the tensions? So we're looking at magnitudes here. So how big are the tensions? Okay, we know that they'll point to the left on one side and the right on the other, but we're specifically looking at the magnitudes here. Okay, how large are the tensions? Okay, and so what is the relationship between the magnitudes of the tensions in each of the strings? So the first choice is T1 is greater than T2 is greater than T3. The second choice is the opposite way around, that T3 is greater than T2 is greater than T1. The third choice is that they all have the same magnitude. And the fourth choice is that they are random, okay, that there's no fixed relationship here. Okay, I might give you a hint on this one while you're thinking about it. So try and look at each block individually, think about all the forces acting on each block, the horizontal forces that would cause the block to accelerate with an acceleration A. And in this case, all three blocks have the same acceleration A. And they're all accelerating to the right. And so what does that tell you about the sizes of the tensions acting on the blocks? Okay, I think we'll do 10 more seconds on this one. So 5, 4, 3, 2, 1. So this one's really interesting because this one was almost a tie. So we've got 70 for A, 72 for B, and 61 for C. And nobody went for D. So nobody thinks the tensions are random, which is good. It's not D. All right, so let's have a look at how this would work. All right, so this is what is the case. Basically, if you start by looking at the mass 2m, what do we know? We know that tension 2 on the right of mass 2m, pointing to the right, must be larger than tension 3 if we want 2m to accelerate in the positive direction. Okay, the force to the right must be larger than the force to the left. Okay, assuming no friction, which we said we didn't say there was any friction, so generally ignore it if we don't mention friction. This would be true even if there was friction, actually, because you still need tension 2 to be bigger than tension 3 and the friction, if you did have it. Okay, and T1 has to be bigger than T2. Okay, those are the only two forces acting on little m. Okay, and we need T1 bigger than T2 for little m to accelerate to the right with acceleration A. Okay, so that means that in fact T1 has to be the biggest one. Okay, because T1 has to be bigger than T2, and then T2 has to be bigger than T3. So even though the third mass is the largest, okay, that third tension is not the largest. Okay, in fact, it has to be smaller than the other two tensions. Okay, so this is again another situation where you've got to look at each of the masses independently. Think about the forces that are acting on each, just to look at them again. So here is mass 2m. Okay, the only horizontal forces acting are T2 and T3. Okay, T2 to the right, T3 to the left. We need T2 bigger than T3. Okay, for it to accelerate to the right. And similarly, we need T1 to be bigger than T2 for mass m to accelerate to the right. Okay, so hopefully that makes sense to everybody. We'll stop that poll. So now I thought what we do for the rest of the class is to look at an example. And this is kind of a classic example, okay, put into a slightly different context now. So what we have here are two children of masses 35 kilogram and 45 kilogram, and they're hanging vertically from opposite ends of a rope that passes over a fixed horizontal metal bar, kind of like a pulley in a playground. If the friction between the rope and the bar is neglected, okay, so we're not going to worry about there being any friction here, and we're going to try and figure out what are the magnitudes of the acceleration of the children, okay? So the idea is that there's a mass difference here, so there's likely to be an acceleration. And we're going to try and figure out the tension on the rope. And if the children start from rest, we're going to figure out how far will each of them travel in half a second. Okay, so that's what we're going to do. So the first two parts of this are a force problem, and then the last part, and this is kind of common with these problems, once we've figured out the acceleration for the system, then we can do a kinematics problem to figure out how far they've traveled. All right, so first thing always, when you do a force problem is to draw your free body diagrams. So here's the free body diagram for the smaller child, mass 1. Okay, and I'm going to define, again, like I usually do, upwards to be plus y. Okay, and so the smaller child, the orange one, has a tension upwards and their weight, m1g, downwards. Okay, so that's our free body diagram for the first child. Here's the second child. Okay, so notice same tension, okay, because the rope is wrapped over like that, okay, both of the tensions are upwards, supporting the kids, okay, and they're both the same size because it's the same rope and there's no friction in that pulley there, okay. But the larger child has a larger weight, so we've drawn the second child, M2, their weight vector, M2G, downwards as a larger. Okay, so there are free body diagrams. Now, the next thing you do is that you're going to start applying Newton's second law. So I'm going to start with mass 1. And right now, we only have forces, and this is true for this whole problem, we only have forces in the y direction. So we don't have to worry about the x direction at all for this one. Okay, we're just going to do the y direction. All right, so what do we have? So our Newton's second law says the sum of the forces in the y direction are equal to what's upwards? Tension. So we're going to have tension, positive T, and then minus, because it's in the negative direction, the weight, m1g. And we know that that must be equal to mass 1 times its acceleration. Okay, and I'm going to write that as a1y, which is the y component of the acceleration of mass 1. Okay, now it's not going to have an x component, but just to be careful, I'm going to call that a1y. All right, now the second mass, the second child, the one with the green sweater. Okay, so same thing again. All right, the sum of the forces in the y direction, which is upwards, is equal to the mass of the second child times their acceleration. So what do we have? Tension upwards minus weight downwards, and that's equal to mass 2 times the acceleration of the second child, right? Which I'm writing as the y component of the acceleration, okay? All right, so that's what we know so far. That's what Newton's second law tells us. So now I'm going to switch over to the next page, okay? So I've got my two Newton's second law equations, and I've got my my two free body diagrams. So what do we do now? Well, we want to try and solve for the acceleration. So the next thing to realize is that with the acceleration is that the smaller child, this is a reasonable guess. They don't necessarily tell you this, so you may have to make a guess here, and this happens sometimes. It's probably reasonable to guess that the smaller child is going up and the bigger child is going down. Okay, so that's a guess to make. So we're going to make that guess. Typically what will happen with these problems is you'll make a guess like this. If you're wrong, say it was really the other way around, then you'll end up solving for a magnitude that's negative, and that'll be a flag for you right away to say, oh, I must have done that wrong. Okay, because I know that the magnitude should always be positive. Okay, and since there's only acceleration in the y direction and no acceleration in the x direction, that tells me that the y component of child 1's acceleration is just the magnitude of the acceleration a1, and the y component of child 2's acceleration is minus A2 minus the magnitude of their acceleration because it's in the downwards direction. And then the other thing that has to be true, if this rope stays taut, is that A1 has to equal A2. The two children's acceleration has to be the same. Okay, so that means that I know that minus A2 is equal to minus A1. So I know that child 2 has a y component that's minus A1, and child 1 has a y component that's plus A1. All right, so now I'm going to plug those in to my two Newton's second law equations. So there I've plugged in A1 for A1y. So I know tension minus M1G equals M1A1. And then I'm going to plug in minus A1 into the second equation for A2y, okay, because I know that the second child is accelerating downwards. And now I'm going to take these two equations, and the thing to notice here, okay, is I essentially have two equations and two unknowns, right? My two unknowns are the tension and A1, okay? And those are two unknowns in both those equations, all right? And this is going to happen a lot where you're going to have two equations and two unknowns, and you want to solve. And in this case, I'm trying to solve for A1 first. You could solve for tension first, that would be fine, but I'm going to solve for A1 first, okay? So first I'm going to simplify this equation on the left. Okay, I'm just going to rewrite it by adding M1G to both sides. Okay, and then I'm going to plug that value for tension into the other equation. So I'm going to take tension equals M1G plus M1A and plug it in for tension in the second equation. So that looks like that. And then I'm going to then just start playing around with moving things around here to solve for A1, right? So now we just have to do a little bit of algebra, put all the A1s on the same size, which looks like that. So subtract M1, A1 from both sides, okay? Then pull the A1 out. Okay, so I pulled the A1 out, and I also moved the minus sign to the other side, which flipped the order of M2 and M1. So right here, now we're just still solving, right? So mass 2 is not negative. Mass 2's acceleration is negative. It's in the negative direction because it's down, and I defined y to be the upwards direction. And so I end up with an expression for the acceleration. Okay, so this is the magnitude of the acceleration for the smaller child, which is also the magnitude of the acceleration of the larger child. Okay, so once you've got an expression like this, it's useful before you go on to see if the expression makes sense. So that we're going to do that before we go on. Okay, so if you have time, it's often useful. So now we're going back to our statement again. Okay, and so this is the expression that we got for the acceleration. So does it make sense? Okay, well, the first thing to look at is we know M2 is bigger than M1, right? So that means that the top of this expression will be positive. And we know M2 plus M1 is also positive. So this is a positive quantity. Does that make sense? Yes, we were solving for a magnitude of acceleration, so it should come out positive. So that's good. That makes sense. Okay. Another way to check whether it makes sense is to think about, well, what if M1 were 0? What if that smaller child had no mass, or what if that smaller child let go of the bar, like disappeared, okay, or jumped down? Okay, what would happen to the big kid, do you think, if the little kid let go? Anyone want to guess what would happen to the big kid if the little kid let go? Yeah, the big kid would fall, right? Exactly. The big kid would fall, and what would the big kid's acceleration? Right, the big kid would fall with an acceleration equal to g. And if you take your expression and plug in m1 equals 0, we in fact get that the acceleration a1, which is also the acceleration of the larger child a2, would become g. So we get what we expect. Okay, that when we set m1 equal to 0, we get an acceleration equal to g. The big kid falls at g. So that's good. That makes us feel better. All right. That the answer sort of makes physical sense for us. So now we can plug in some numbers. So that makes us happy. There's our happy face. All right, so now we're going to plug in some numbers. We plug in our two masses, we plug in our g value, and we get that the acceleration here of the system, okay, this is the acceleration of both children, the magnitude here, okay, upwards, remember, on mass 1 and downwards on mass 2 is equal to 1.2 meters per second squared. Okay, so, and that's a, you know, not a huge acceleration, which is probably about right. All right, so now we want to figure out the tension. So now we go back and grab our expression where we solved for tension, which was m1g plus m1a1. And we basically plug in our numbers again, our 35 kilogram and our g and our a1, and we get that the tension is about 390 newtons. Okay, notice that that tension is bigger than the weight of the smaller child. And if you think about it, it's got to be bigger than the child's weight if we want them to accelerate upwards, right? We want to have more force up than down if they're going to accelerate up, okay? And it's also, if you calculate it, it's also smaller than the weight of the large child, which we also want because we want the force downwards on the large child to be bigger, okay, than the upward force on the large child. So that also seems to make sense for what we want, okay? And then we're going to do our kinematic problem, part C, okay? So we want to know how far will they each of them travel in half a second if they start from rest. So now we go and back to, they give us a time, so we're going to use position as a function of time here, okay? Let's do this for the smaller child. It works for both of them because however much the smaller child goes up, the big one will go down, okay? And we're going to say the smaller child starts with position equals 0. He starts at rest, he or she starts at rest, so their initial velocity is 0, and so it's just going to be 1/2 AYT squared. Okay, so just 1/2 our 1.2 meters per second squared times our half a second, and we get about 0.15 meters, which is 15 centimeters. And you think about 15 centimeters, it's about not very much, and that seems like a reasonable distance, right? That probably in that first half a second, right, where you're starting from rest, you're not going to move very far in half a second, okay? And yes, you could use either child to find the tension, okay? I happen to use that expression because that was the one I solved for, but you can use either one, and that's a way to check your answer, okay? We can go back and look at the other expression here. Oops. Go back to our previous page. I'm going to go all the way back. All right, so we did have another expression for tension here, right? We had tension minus m2g equals minus m2a1. So you could have used that one to solve for the tension. That would have been fine. Okay, either one of those will work, and you should get the same answer. So are there other questions? Okay. I mean, somebody was asking why does A2 equal minus A1? And it's basically because the two kids have the same acceleration, but one is going up and one is going down. So I'm going to stop recording now, but if anybody has questions about the test, I can answer a few questions right now.